Thank you, Marcus, and thank you for coming. So I'm going to talk about the TLA plus specifications for the client-facing side, the consistency guarantees that Cosmos DB provides to the clients. Okay. So this will be a straightforward talk. In the first part, I'm going to motivate the benefits of modeling with TLA plus, and then I'm going to define what is consistency in the context of distributed databases, Cosmos DB, and then I'm going to ease our way into this. So first I will start with a single client specification of TLA plus, specification of the consistency provided from the distributed database, and at the end I'm going to talk about the general specifications with multiple clients, putting the Cosmos DB to test with respect to consistency guarantees provided. So if you worked on any large software system, you know that these systems are prone to corner cases, failed assumptions, race conditions, cascading faults. Corner cases are there because there are a lot of parameters, and these parameters interact with each other in unanticipated ways. Failed assumptions are there because your environment is also complex. Your environment is made of other components that also has parameters and that also interact in unanticipated ways. So your assumptions about the environment also fails. So some examples of this is sometimes you say that single hop communication is faster than two-hop communication, but it turns out that two-hop communication returns faster than single-hop communication. Sometimes you think that talking to the same process on the same machine is faster than talking to another process. Well, you have a problem. What you think was, what you thought was an atomic block of execution is not, right? And race conditions are there because now all of these systems are concurrent systems because with the prominence of microservices, etc., you are in the multi-threaded world, you are in the concurrent execution world, and you have problems due to race conditions. And cascading faults are there because the fault paths are not very well exercised, not very well tested. You develop systems, it's complex because of these things, and human brain reasoning can only scale so far. There are enormous number of paths that these can take. And this leads to problems in the deployment. So today, even people suggested testing at the deployment, testing at production, right, with chaos engineering at all. And those things are nice. I'm going to talk about how they also fit with a model-based design and debugging testing. But often when you get something out of them, it's too late. It's very late to change your software system because you invested a lot into it, you made a lot of decisions going that direction, and costly changes, if at all. But if you model first, you can save actual time, not lose time. Some people say that if you model first, well, we are starting on development late and it adds to the development cycle. Actually, we argue that it saves you time. You can finish faster because it's going to prevent you to embark on failed implementation attempts, right? Futile development efforts. If you model at a high level and debug your model, debug your design exhaustively, you can catch the errors at design time before it's too late and first fix your design, then embark on development. This gives you clarity of thinking as well because you understand exactly what you want to do at the specifications level before you embark on the development. This is also very useful during the development stage, because this gives you something precise to communicate the design with your team and with your clients as well. Finally, when you are having a high-level design and going to lower levels, you can treat this as a refinement process and figure out alternative ways to implement the same thing. Because at the design, at the model level, we are thinking about what instead of how. You make that separation, and when you are implementing, you can say, actually, for these environments, maybe I can implement it differently like this or differently like this. You can see those trade-offs. And TLA Plus is a framework for modeling systems, especially distributed and concurrent systems. It's formal language and framework around it, designed for describing and reasoning about practical distributed and concurrent systems. It's developed by Leslie Lamport, Turing Award winner 2013. Leslie has been using it, I think, going back to 1980s, the TLA Plus notation, but model checker became available only in 2008-ish? 2000s. Okay, 2000s. And right now it's mature, it's being used. I'm going to talk about some examples of its use. It's developed to be practical. It's based on simple math, basic logic, set theory, some temporal logic, and the best thing is it's supported by a model checker. So the math-based formal language enables you to model at a high level, but with precision. And model at a high level means at an abstraction level where you talk about what and not necessarily how it is implemented. This requires some getting used to. This is abstraction-based thinking, maybe more declarative thinking than operational thinking. But math enables you to do that, specify the behaviors at the what level precisely. In English, you can also, right now, what does the industry do? They give these specifications in English, but English is ambiguous. And it's operational reasoning, which I will talk in the next slide, that has a lot of handicaps. And TLA Plus has a syntactic sugar on top called Pascal. It's a pseudo-algorithmic language. It provides ease of use and readability. I have been using it in my classes since 2014, and students are able to pick it up quickly. In my experience, Pascal is easy to pick up and use. And as I said before, the integrated model checker is great because once you come up with your model, it checks your model for the invariance, which I will talk next, debugs it exhaustively. It says that, what if this operation and this operation, then this operation happens? Or what if this? It goes through this tree, debugs it exhaustively. It spits out counterexamples to your invariance and show how those could be violated by collusion of, we talked about this before, collusion of the concurrency, collusion of the failed assumptions, collusion of corner cases. Okay, so let's talk about the invariant-based reasoning. The prevalent way of talking about design is right now operational thinking, happy path operational thinking. So in English, the specs will say, well, this happens, then this happens, then this happens. It talks about the happy path first. And then it says that if one region fails, then this can happen, this will kick in, etc. Then it starts to enumerate about what can go wrong and how it is taken care of. Right? But as we discussed, this enumeration can get very complicated. There are a lot of cases that you are going to omit some cases. So the invariant-based design says that don't start with happy path operational thinking. Just focus on the invariance, what needs to go right, what invariance your system needs to satisfy, and show that these properties follow from those invariants. So this way of thinking is the TLA plus way of thinking. So this helps you avoid complexities and bugs of operational reasoning for concurrent systems. And distributed systems researchers are, when you are a PhD student, you quickly learn this way of thinking, because even for programs for 3-5 actions, you see that, well, the human mind cannot scale to that. There are a lot of hidden complexities. You should have more discipline of thought through these invariants. And these invariants are specified as safety and liveness properties easily using the TLA plus math notation. And safety says that nothing goes wrong. Liveness says that something eventually goes right. Again, you can see there is a separation of concerns. So we talked about 2 levels of separation concerns: what versus how, right? Specification versus implementation. And at the specification level, safety versus liveness. Nothing goes wrong, and something eventually goes right. Something eventually happens. Okay, having talked about the invariance, I want to take some time to talk about this operationalizing TLA plus. So when you have your system, you try to figure out an invariant. You play a game with the TLA plus framework. You suggest some invariants. You suggest a model for your system. TLA plus model checker exhaustively tests it and says that, well, your invariance break for this counterexample. Then you go back and then you say, okay, maybe the protocol should be slightly modified like this. Or maybe I should modify my invariant like this. But you make some changes. Then you exhaustively debug that new model and new invariant again. When you converge to something, then you say that, okay, does this invariant, from this invariant, safety and liveness conditions, what are the other safety and liveness conditions that follow, and is it okay for my requirements, for my software, with respect to its obligations to other components, etc. And the nice thing about this is, when you're done, you keep the model. And today the software is unavoidably extended with more features, etc. When you need to add a feature to the system, you don't jump onto embarking implementation to implement this feature. What you do is you first add this feature at the model level, at your TLA plus spec level. Then you see, okay, does it break my invariance? Does it still satisfy my requirements? If not, you tweak the protocol or you tweak the invariance, but you first debug your model. You figure out what's the correct way of adding this feature. Then you embark on implementing this. And this is how it helps in the development process continuously. So basically this third step suggests that even when you didn't start with a model and went to implementation for your system, it's not late. You can still have a model for your implementation, large system, maybe even at different levels of abstraction, and that's still useful because first, debugging at this design level, maybe you will catch bugs that did not show up in the execution so far, but will eventually show up someday, and you get prepared for that. Secondly, you can, when you add, when you need to add features to your system, you can first add it to the model and continue from there. Okay. So TLA Plus has been used in the industry. In 2014, Amazon Web Services had a nice paper detailed their use of TLA Plus in their systems, services, and how it helped them. I think there are other reports from Intel and Microsoft for using it in terms of some hardware systems. Right now, I'm at sabbatical at Microsoft Azure Cosmos DB. It's the Microsoft's globally distributed database that's operating over 50 plus regions across the globe and provides distributed data store and distributed database to several, many heavyweight enterprise customers. TLA Plus has been used in Cosmos DB throughout its start, and replication protocol is modeled in TLA Plus and tested for correctness against failures. Today I'm going to talk about only the client-side facing of multi-write region model for Cosmos DB. What are the guarantees it provides to the client without talking about the implementation model. We also have a model for the implementation which we tested to make sure that things work before embarking in implementation, etc., and catching problems at the design level. There are other places TLA Plus is used, include the CRDT modeling on top of this Cosmos DB to provide conflict-free replicated data types kind of applications, and least protocols that are used in Cosmos DB at one level of abstraction. We also model it to figure out what, to catch problems, basically, to figure out what needs to go right and go from there. So before I talk about the single client specification and multiple client specification, the guarantees provided to the clients, I first want to take some time to talk about what is consistency in the context of distributed databases. So consistency defines how the database behaves when a client is reading, writing, while other clients write at different replicas. So this is a distributed database. A client is reading, writing, but there are other clients that are reading, writing at different replicas in this region and different regions. So what type of guarantees do you give to this client? How do you order the writes with respect to each other? What do you return for the read and write when there are other writes in the vicinity? So this is all goes under the consistency guarantees. In general, the tighter consistency guarantees the database, distributed database provides to the clients, the easier it gets to program and develop applications on top of this distributed program. But there is a trade-off, right? The tighter guarantees you provide, that means the more overhead, because the replicas need to synchronize more often and make you wait for your request. And you do not always need it, right? Depending on your application, you may be okay with using something more relaxed and faster, or more tight guarantees you build on. But even for these tight guarantees, at the developer level, we also have models to figure out ways behind the curtain how to provide the tighter guarantees more efficiently without introducing any errors. Okay, so going back to these consistency guarantees, Cosmos DB tries to cater to all these needs the clients have. Some of them will require strong consistency. Some of them will say, okay, my application does not require that much consistency. I care more about faster responses, so this is good for me. And Cosmos DB provides 5 well-defined consistency levels, and in the specs, I'm going to talk about what these levels are.
How do clients use among these?
They look at documentation. They try to figure out what works for them. I can give you some numbers. Session consistency turns out to be most popular. Okay. 70% is session consistency. Couple percent is strong consistency, the highest consistency level, and the rest is divided between these.
Can you say what session?
In a second.
Oh, okay, thank you.
So here is the English description of them. Obviously, this makes reference to some other words you may or may not be familiar, and is also ambiguous, which is a good segue in the rest of the talk, which we will, in TLA Plus, we are going to show from the client perspective what these mean with respect to the writes and reads the clients have. So strong consistency provides the strongest guarantee. It provides linearizability, meaning that all of these writes are ordered in the same way at all the replicas. And when you read from the replica that you chose, maybe the one that's closest to you, you are going to read the last acknowledged write on any replica. So this is a distributed database. So you are going to read the last acknowledged write on any replica. Let's say that this client talked to this replica, got a write acknowledged. Maybe it's the same client now talking to this replica, so you need to give it. Right? Strong consistency said, whatever the distributed database acknowledged as write, I'm going to give for the next read after this. So it's giving a single system, almost single node, abstraction, single node guarantee. But of course, this requires a lot of synchronization between the replicas and is not always the most desired option. Bounded staleness relaxes this a bit. It says that this read is going to get maybe not the latest replica, not the latest write that's acknowledged, but within k of them. Right? If there were 3 writes, this is going to give you not older than the last 3 writes, or not older than the last 3 seconds. Right? So it relaxes this. And you can think of strong consistency as the staleness of k is equal to 1, meaning that don't give me anything staler than the most recent write. Right? So you can relax it with k is equal to 3, 4, 5, etc. This is across clients. This is across clients. Session consistency says, let's focus on single client point of view. From the client point of view, can I read my own write? If I wrote, next time I read, I don't care if somebody else got another write acknowledged. I at least want to read my write. Why is this hard? It could be hard because in one region, you also have multiple replicas for fault tolerance regions, and you may be routed to another replica which may not have your write, which may not have time to replicate to the other replicas in the same region. Okay? So this is session consistency. This is client-centric. The others are also not client-centric, again, across clients, but these are more relaxed. Eventual says that, I can read you anything from the history, maybe even you do a read, I send you something, in your next read, I can give you even an older value. How? Because for your first read, you hit this replica, which has a more recent value. For your next read, you hit another replica, which has a staler version that didn't get this write replicated to it. So consistent prefix is similar, but it says that, well, the replicas are getting these writes without updates and gaps. Okay, so this is hand-waving discussion of these consistencies, but with the TLA plus models, now we are going to get into more detail, and we will get a chance to see TLA plus in action. So to ease our way into this, we start with saying that, let's say that there is only single client, and database, we model a single process. What does these consistency levels mean? Okay, so this is Pascal. This is very easy to read because it's pseudocode. You can understand things going on. So this is a client process. We have an op count. We try to limit the op count to maximum op count. Let's say this is 10 because we want to keep the model checker. We want to give the model checker a finite space to test all these things. This is C history, the client-side history, that we will add things to be able to check our invariants and properties with respect to these consistency specifications. So this client loops through this maximum of times, and maybe this is up to 10. And at this point, maybe you can have a question, is 10 enough? Practical experience suggests that since TLA plus looks at all possible ways of things can, all possible ways of ways that this computation can continue, if there is a problem, it will find in a short number of operations. Then after you get confidence, you can try higher things and more exclusive, more exhaustive checks. So we increase the operation number. We send to the cloud, the database, a write operation. So we are saying, I want to write for the data. Let me write the operation. So initially it's 1. This is session token only used for the session consistency, ignored for the others. And then the sender is myself. Okay? And then this is sent to the database. Then this client just waits here to receive an acknowledgement. After it receives an acknowledgement saying that, okay, my write is completed, it updates the session token. This is only used for session. So it sends to the client this time a read operation with the consistency type as specified. We can change this at the model checker with the consistency. And then the read reply is received. The client waits to receive for the read reply and appends the read reply only the data from the message to the client-side history, because at the invariant check, we are going to do some checks based on this history. Clear so far? Any questions?
So this is sender receive stuff, is that kind of how you have to
Right, so it's all in math. So this is, it's in our file. You can specify it very easily. So the way we model is, channel is per process. Process 0 is database, and you can have up to, clients. We have one client for this one. And it maps them to a queue, a tuple, right? Basically, channel is an inbox at each process. When you invoke the send operation with a destination process ID and a message, it's going to say that channel is an array of these inboxes. It's going to say that, well, for the inbox of the destination process, just append this message to that inbox. And for the receive, you first block to say that the inbox of that process has something to receive. Then you take the head from the channel and set the channel to be the tail of itself. So this is at Pascal, easier to read. And then this is then compiled to TLA plus. I will show you the TLA plus code for this. And at the beginning, you also define constants. And the constants that you don't define, like maximum, etc., that you didn't give a value for, you can give the values at model checking time, and so you can test with different values. Yes?
So this model doesn't allow, this model is modeling instantaneous delivery, but it doesn't allow messages to get delayed in the network and then reordered by the network.
This doesn't allow reordering because this is FIFO. If it is put, well, this doesn't.
Well, TCP allows I buy FIFO between two endpoints.
When you have multiple processes, the model checker is going to try all possible interleavings of the message. right?
Yeah, but this
so
doesn't
let's say there are two processes that can send you a message, right? It will first execute this process 1, then it will show you a scenario where the process 1's message is received, put into your inbox queue first. In another execution, it will try process 2's messages put into your inbox queue first. So it's going to look at different ways of, it's going to add the concurrency itself. But for my modeling, I'm just using FIFO channels.
But this doesn't, so it's possible that, so there's two processes sending to you, let's call
Yes.
them A and B. So what if A sends me a message, then sends B a message, then B sends me a message?
Yes.
Your model only allows B's message to arrive at me after A's message.
That's correct. That's correct.
But in reality, B's message might arrive at me.
That's
before
correct.
A's
You can't have labels in the macros, and you're implementing this non-determinism outside the macros by putting the labels, and probably we'll see this later.
No, but for the scenario you said yes. But you could do it differently. This is only one way of doing the channels.
Right.
You could also do it differently by adding delay. Yep.
You
It's
could
mad.
just have, or you could just have receive any message in your queue. not
That's
just
that,
add.
that's right. So the math gives you different ways of treating this. Right. Exactly. This is the database model.
See the labels now?
Very simple. It's a distributed database, but if there is one client and we are saying that, okay, let's just focus on talking about these consistency things, we are just going to have a very high-level model of this database just with one process. It's in a while-true loop. It just reacts to the messages it gets. If this message is of type write, it's going to append it to the database. There is a single database here. We are at a very high level of abstraction. And then it will send an ACK back to the sender. But if this is not a write, this is a read, it's going to look at the message type, and it's going to, based on the consistency level, it's going to emulate, if I had multiple replicas, what is an acceptable reply from the database I have seen so far, from the writes I have seen so far. For eventual, it will basically send any value in the database history so far. Because there could be a replica that didn't get the latest replicated, it will send that value back to the client. So on. For the session, it's going to send something with the staleness that's limited to going back to the session token and not earlier. So it will say, this guy gave me a session token. From my database history, I can only give something at least as stale as the session token, no staler than that to the more recent ones. And for the strong, it's going to always give the most recent, right? For the database, for the bounded, it's going to say within the last K, make sure that I return this.
Which is a log.
Right.
And the way you're simulating the replicas by basically just choosing different points.
Exactly,
of the log
exactly.
So you
Right.
have one database, but you're simulating.
right.
You're not modeling the replicas explicitly.
Right. There are different.
Yeah.
This is the simple model. Next, I'm going to show you the more general model where you have a database per region and each one can reply themselves.
So is the goal here to eventually have this match the real implementation? Just modeling what they say
Our goal in
actually?
the specification is to tell the client when you say that you want strong consistency, what do you expect from us? Right? Just to communicate to the client. We also have the internal representation of this from developer perspective that we use to debug and to figure out things go correct. But this is the customer-facing spec. We are just saying, when we say we give you eventual consistency,
So you're
what
comparing
you should expect.
this model, which is a approximation of what you think the database is actually doing.
Right.
And you're comparing this against the English specification
Yes.
that you have to make sure that the English informal stuff actually
Right.
is satisfied by this.
Yes. Right.
So I have one
Basically
question about-
clarifying the English specification
Okay.
with this.
So I have a question about the eventual consistency. So that's a liveness condition. I don't see how you can
yeah.
prove that.
I may not have it. We model it with one database here, so we don't talk about the convergence of the replicas, but when I go to the general specification, I'll show you how we model liveness. Basically, we say that eventually, always, all the replicas have the same last state. So that could be an example of liveness condition. They converge to the same database. Yeah.
So are you modeling infinite executions for that, or are you somehow?
No, again with a limited number of invocations from the client.
Okay.
Up to maximum. I'll come to that in the second one. Okay, so these are invariants, how you write invariants. So we put these things from the client observed state in C history. Now we can say, does the C history, how does it relate with respect to the database? At any point, invariant says that at any point this is satisfied. And these are all safety, as pointed out. These are all safety that we are discussing now. So eventual says that, well, whatever is at the top of the C history, it should be in the database. It doesn't come from anywhere else, right? Session says that whatever is at the top is has some recency. It's at least as fresh as my session token, not staler than that. Strong says that whatever is at the top of my history is at the top of the cloud. But figure out, I want to note that this is pointing to PC1 is equal to CW. What is this? This is the label. So this is basically saying that at the point the client finishes the read, before it started its new write, then I check this. Because even with a single client, right? If I write something, now my C history and the database history is at odds if I'm looking for strong. So I need to check it after my read before I write something. Right, so that's that. So let me actually go to the TLA plus toolkit. I will start, this is this one. So this is the entire spec. This is in Pascal. And then you translate this by pushing a button Command-T, translate it to the TLA plus. TLA plus is more logic. This is what gets executed by the model checker. So it's easier to write the Pascal and get it translate to the TLA plus. But if you have some familiarity with reading TLA plus, it helps things to figure out, oh, is the translation what I expect it to be or not. Basically, this is math at the TLA plus level. So it says that next is either select the cloud thing and then execute something. And it's a formula. It's a logical formula. Either this or this or this or this. And each action is basically given as this state or the next state is equal to this state kind of way. It's in logical formulas. You don't have to know about them mostly. But when you write Pascal, it compiles into this. And this is what gets executed by the model checker. Right? So the spec is init and always pick a next action. And then it becomes or this, or this, or this going on. And after the translations, this is automatically done. You also have your invariants that you check. To check the invariants, you open a model. You populate the model, the parts that are not... okay, I'll zoom into this. So this is these are the constants that I didn't assign any value. Now I can assign values to them. And then I can say that what invariants I want to check. I can enter them myself, and because I wrote them in my spec, but I can write here. I can uncheck it or check it to change what I want to check. And then this gives the counter examples for things, right? So I think okay, here I'm checking with consistency eventual. And I'm also checking for, is the strong invariant violated? and then let's push the model checker. The model checker runs all possible executions of this model with the eventual consistency. Of course, this is straightforward thing that it says that, okay, there is one error. I found that using eventual violates the invariant strong, which is expected. So let's collapse the error trace and then go through the error trace. Okay, initially database 0, operation is 0, C history is 0, and we start. So what's going on? In the channel of the zeroth process database, the client has put a write operation with data 1. Okay? This is originating from the client. This is consumed by the database in this thing, and it's added to the database. Okay? Then what happens? The database puts to the channel of the first process a message saying that acknowledgement message. Okay. Now the client is going to put a read message to the database's inbox, right? With eventual. The client is doing an eventual read. And this is going to be replied by the database. The database sends a reply. Since this is eventual read, it's giving a 0. It can give a 0. It could have given 1, and it could have given 0 as well. So it's giving 0 as the answer. So the client is going to take this, put it in its C history. Now its C history is 0, 0. And now the invariant is violated because the top of C history, when PC is CV, doesn't match the top of the database history. So this is an example where this thing is violated. This is straightforward, but I just wanted to start with straightforward example first, right? So let's make this strong so that we check that all of those invariants are satisfied. Okay, it says deadlock reached. This is expected because while the database in a while true loop, it just reacts. The client is in a finite number of operations. And when the client is run out of operations to execute, that's the deadlock. I just wanted to show this to say, well, what's the trace when we are writing consecutively and reading them? This can get long because we separated the send, acknowledgement, receive, everything with a message. Okay. So let me animate this, and then you can keep your eyes on how the database and the C history change with respect to each other. Okay, 0, 0, send the write message, 0, 1, acknowledgement sent, strong read is sent, and then reply is sent with 1, and this will be added to C history. So 0, 1, 0, 1. I'll speed up. 2 is added to the database, 2 is read at the client side, 3 is added to the database, 3 is read at the client side, etc. until this finishes, right? This is not a counterexample per se because this is where deadlock is reached, but you can see how this played to execution, to end, termination. Okay, so back to this was very straightforward, right? So let's do maybe just a simple change on this now that we have it. Let's say that this single client now reads from the, not just increments operators and send to the database and read from them, but now it just reads the value first from the database and writes the value. Then reads the value, increments, writes the value, and so on, right? So with these consistency levels, what do you expect would happen? For the strong consistency, you always read the most recent one. So if it's a 0, you will read it, you will write a 1. When you read next again, you will read 1, you will write 2. It will be consecutive in the database history. But not necessarily with bounded and eventual, right? So we are going to look at that behavior. For session, it's also, you get consecutive because session says, read my own writes, right? For this, if there is single client, this also works. And for session, you also get a consecutive database. So this is the client just slightly modified. The rest of the model is unchanged. We modify the client so that the client first sends a read operation to the database, receives the reply, adds it to the C history, takes the value, increments it by 1, and writes back up number of times. And then this is some snapshots from the what model checker spits out. For strong, we see that, yep, database is written consecutively, and C history matches that. But for bounded, for example, what happens is this reads 0, writes 1, reads 0 again, because bounded means the last 2, with k is equal to 2, right? So writes 1 again, reads 0 again, puts in C history, writes 1 again. Now the bound has moved. Next time it reads, it's going to read 1. And then next time it writes, it's going to write 2. But it reads again 1, because the model checker is going to give you as stale value as possible. So you see that the database is not written consecutively, right? So, okay, let's go to the general specifications before to show more complex behavior there. So this was with single client. When we have multiple clients, we are in a problem, because even with strong consistency, I write something, I write 5. I want to read again. But it's not, there are other clients. They could have written something else. So if I don't read 5, does this mean that the database is broken? It's not providing strong consistency? I have no way of knowing, because with multiple clients, even after I write, I read immediately. Maybe there were other writes that get scheduled and I don't know about them. I can't test the database. So the multiple clients need to share a back channel, secret, to test the database with. This is actually how linearizability checkers work. So the Jepson linearizability checker, it spawns multiple clients and sends read and write operations from these clients. So tracks this in the log, the order it is sent, tracks the replies back, and then checks for linearizability over that log. So in our model, so we are going to make the clients share a secret. This is the value, and this value is a shared variable. This is at the modeling. So I can model at the high level. My clients are sharing this secret, its value. Maybe implementation of it, if you have really precise clocks, would be a real-time, right? Real-time clock, right? So you record when it is sent, you have really precise clocks, and you look at the replies back, and you check if the database is satisfying your satisfying the consistency level it says it is. So sharing this secret multiple clients across different regions is going to put Cosmos DB to test with respect to these consistency guarantees it provides in the presence of concurrent reads and writes. In this model, for brevity, we use shared memory instead of message passing. We will directly add this thing to the database and read from database. But we are going to now model the database with multiple regions. Each client is going to write and read in their corresponding regions. The writes will be appended, so if I'm a client at region R, my write will be appended to the database at region R, database R. These databases at different regions perform an anti-entropy process where they merge their databases. my model is not going to talk about how we implement it at the back end, but it gives you the end result of implementing it for a maybe last writer wins conflict resolution, because it's going to merge these databases with happened before relationship. So here is the client. Now you are familiar with this notation. The client is saying that, well, again, this is model checker. I'm going to model check, so I want to keep the state space finite, and numop is less than max numop. Increase the numop. Either do a write or read. This is non-deterministic. And the model checker is going to be a jerk, basically, and it's going to look at all possible things. And if there is a possible execution that violates your invariance, it's going to spit it out as the counterexample. So I'm introducing non-determinism here. Either increment the value and write or read. And the macros for write and read, this is shared memory model, not message passing model now. And it gets more succinct to write it this way. So the write, it says that the invoker, the client, self1 refers to the client's region, okay? If the client is in a write region, which I can control in the model, make all the regions write regions. If the client is in a write region, then it's going to append this write, the value that the client proposed, to the database at that region. Self1 is the region of the client. Database R, this is appended to the database R. And the history is again like the C history in the simple specification. The write is now added to the history, so we will do the linearizability test. The invariant checks over this history, comparing it with the database as well. So history, we add this operation. We wrote with this value or at this real-time clock, etc. And we update a session token. What is this? This is to throttle some of the writes. Okay. Why do you need to do this? You need to do this for strong consistency and bounded. But for the others, you don't need to do it. Basically, bound, I'll show you the full spec. We will go through it. For strong consistency, bound is 1. For bounded staleness, it's K. For the others, it's basically infinite. You don't need to wait for the replica. You don't need to give time for the replicas to synchronize before you do your next write.
Is that an assume then? It blocks execution?
Yes. It's a await or when statement. It blocks execution. It says that do this only when this is true.
Okay,
so this will come as an conjunction before the rest of the formula. Okay, and the read, again, we have some preconditions. If the consistency check for a session, make sure that the database at this region is up to that staleness value, up to that freshness value, right? Database in the client's region, the last item is fresher than my session. Otherwise, I won't allow you to read because I'm providing you session consistency. If I'm providing you session consistency, I'm going to make you wait for this. If I'm providing you strong, I'm going to make you wait that all the databases at regions had time to synchronize. They have the same last value. And then you will be able to read from your region and put it into your history and so on. Now, the database is really simple. It's a database at each region. So if I define 5 regions, there will be 5 processes all doing this. It's a while true loop again. The database is going to select another region's database, and it's going to do anti-entropy. It's going to say that merge our databases, satisfying this less than relationship to stand for happened before with respect to our logs. Sort seq is a sort sequence library function that you get, and you remove the duplicate things, and this is my new database. It's just anti-entropy. I don't show you how it is implemented. I'm showing you the mathematical succinct representation for the last writer wins case.
So the database here is a set of writes that have timestamps on them?
That's right. Yes. Yes. And it's an array, so for each region you have a database. And then if you are region 1, for example, you pick some region. Region 3, you combine your databases, do entropy. That's how the...
before is defined where?
This one. This is the less than operator.
Yeah, but less than what?
Less than on value, which is timestamps. You can think of it as timestamps, yes.
Oh, okay. But where do I see that? I mean, where is that defined?
I'll show you. I told you about the secret that's shared between the clients. That's the value.
Yes.
Value is a shared variable across the clients.
Okay.
Regardless of which client is chosen for execution, value is incremented. It's a global variable for the model sake. Okay, let's jump into the... I'll just show you...
Though, but the timestamp used by the database mechanism could be different from this real-time clock that the client uses. I mean, that's a possible source of bug.
Right. Right. This is just to show from client perspective. When you have... This is complicated, right? You are a client. This is a multi-region database. From client perspective, when you have multi-regions and you are writing to your writes and you have selected from Cosmos DB this thing, what do you expect to receive? This
Okay,
shows that.
client perspective.
Right.
Okay,
From the database perspective, we have detailed models where we check for our implementation. And ours would be state consistency invariance mostly. This is, if you notice, operation consistency invariance about session, strong consistency, client perspective, operation consistency invariance. So you can define things like monotonic as a function. It says that from the domain of history, whatever indexes are there, choose an index I and index j. If I is less than or equal to j, this implies that, well, its data is less than or equal to the upcoming index data, right? This defines monotonic. Then what you can do is, in math, you can write these things. So you can say, filter the history with respect to reads, and from this region only. And pass it to monotonic reads to check monotonicity with respect to region, right? And you can say, filter the history with respect to reads, and from this client perspective only. Then pass it to monotonic reads to check that we give the monotonic reads per client guarantee. Write for region similar, read your write. You say that if I is a write, j is a read, and I comes early, and it's the same client, then do we provide this guarantee? And the model checker can check all of these. And from these lower level primitives, you can build the higher level primitives like linearizability, bounded staleness, to say the last values in the database at regions are within bound, consistent prefix, session, per client guarantees, and eventual guarantees. So let me go to, actually, to give you a better look, let's open this. Okay, so clients are processes. They, for their ID, they have two parts: the region that the client is in and the client ID for that region. Servers are processes, the region that they are, and server process ID for that region is 0. So in this model, we are saying that, well, one region, one server per region, but Cosmos DB, you have multiple replicas per region. We abstract that away. History, you are familiar, client operation history. Database, now database is an array because we have these regions. It maps to empty queue, empty tuple at the beginning. This is remove duplicates definition. You can define things, the set data structure goes a long way. the last we define as pass it something. It's going to look at if the length is 0, it's going to return you 0. If the length is greater than 0, it's going to basically give you its last element, right? So if you pass it database, it will give you database last element. If you pass it history, it will give you history's last element. This is the write. I covered the write. Read and client. I covered the client. So it's basically that's the entire code. Then you translate it. It gets translated to the TLA plus code where it gets checked, and you have the invariance at the end, and you add a model to it. I had created a model, so I'm opening it, where you fill in these values for num right regions 3, num regions 3. So all the regions are right regions. Bounded staleness constant is 2. Let's put 1 client per each region. Let's limit the maximum to be 0. So invariant is basically basically switching what was the consistency selected and forwarding it to the corresponding formula. But you can also put those formulas here yourself and check for some other things. So here I violate the invariant. Why? Because I say, okay, let's go with consistency eventual. If I ticked off basically just invariant, it was going to check the eventual itself and then it will say no violation. But now I know that for eventual read, I want to see a counterexample where the consistency is violated. So let's run it. TLA plus is quick to figure out counterexamples. So we got our counterexample. I'm going to collapse the trace. I'm going to come here to show what's going on. So database, 3 regions, database at 3 regions, they are empty at first. History, this is the linearizable, this is the clients all write to this one, right? Shared memory, all write to this one. And also I promised to show the value, right? So let me show you value first. Value is basically, you can think of it as a global variable at the algorithm level, right? Value is this one. It's used across the clients. It's you can think of as real time because we are cheating. We are assuming clients have access to this secret back channel, so we can test the database exhaustively. So let's get back to the model view again. Let's see what's happening. Database is initially empty. Client at region 1 does a read. Okay. Client at region 2 is doing a write. Right. In this case, the write, even though the read was invoked first, that's fine. The write is put into history first because this write started first or completed first. It writes 1 to region 2 database, right? So now the region 2 database has 1. Okay. Now we are going to get the read from region 1 database. It's going to return 0 because there is nothing there and strong consistency will be violated. So, yep, when this read is finally returned, it's returning data 0 for it because this database is empty. This is example of how the this thing is violated. Right?
So you said that would be an example of eventual?
Oh, yes, yes. Thank you for reminding. So the model guarantees this thing, but we check for it for saying that writing a liveness condition like this. We can say that eventually always for all ij in regions, database I is equal to database J. The databases become the same, right? Because they consolidate. They keep doing anti-entropy. They will differ, but eventually says that after the operations are completed or after their anti-entropies are consolidated, they will become the same. That's as easy as checking for that, right? What else I want to show? Let's show for session here as well. Let's change this to session, and let's show how the strong is violated again, because we selected strong. Oh, yeah. And there are things you can do here, like say, for worker threads 90, etc. And there are other advanced options. You can even run this distributedly. Okay, it found the error, says strong is violated. Again, probably very similar error, right? So write and read, the write writes 1 with a different client, the read returns 0, same, similar example. Okay, so basically this is all I had for discussing today, the client-side facing invariants for Cosmos DB. And for more information, these specs are available here. Consistency levels, English description is here. TLA plus resources are available at Lamport's website. There is a user-friendly introduction to TLA here. And I can answer if you have more questions, or we can go back to the spec and I can answer your questions about the spec here. Oh, yeah.
Will the specification eventually be integrated into the official doc.microsoft.com documentation?
Oh, yeah, we put it in GitHub. I think it's referred to from the documentation. But yeah, probably that will also get integrated with the uphold of documentations. Yeah.
Are user expected, end users of Cosmos DB expected to run TLC to understand the TLA plus specifications?
Right. So basically, just by looking at the Pascal is not hard to understand, and just by looking at this, you get some expectation of what is provided. If you can run it, you can see it in action. That helps a lot. I mean, that helps my students a lot when we discuss an algorithm. We also give the Pascal code for it, and they change some parts, and they say, okay, actually, when you change this, the algorithm breaks, and how it breaks, you see it. That's useful. So for this, it also helps us. It also helps us. We have the developer side model, and whenever we are in doubt, we can run and check what's the expected behavior.
I have a question about linearization.
Yes.
So we have this global history.
Right.
In the global history, we put the information when the client receives the result.
Yeah. Yes.
But the client might send a request for read
Yes.
and get back a result, and the number can be higher than the other client just because the time that the message passed.
Yeah. I think we steer away from that problem because we just use direct memory read. Yeah.
How do we do this if we have a message passing?
Right. I think a linearizable checker does this by just adding sequence numbers and following this sequence number. Because you host all those clients in one machine, then you add sequence numbers, and you add...
I know how Jepson works, but I have this difficulties to represent this in TLA plus unless I first collect the history, and after that I try to linearize it.
Right.
And I think TLA Plus might not be the best option for that. I mean, it will take forever for any meaningful.
Right. I see. So we also, we also represent the read operation as atomic, right? If it took some time, so what would it be? It should depend on what's the reply time.
Yes.
Yeah.
Okay.
I can send you a link. There was a recent work on that. I will send you a link about that.
I would love to take a look. Yeah. Thank you.
So do you do research and model checking?
No. I'm model checker expert is Marcos. You can ask any question to him.
What are you working on?
Distributed algorithms. Yes, actually, I forgot to tell. I develop like wide area network Paxos algorithms. Always more efficient algorithms are possible at wide area network because Paxos has this limitation of round trip thing. So we develop algorithms that tries to do this more efficiently using flexible quorums ideas. We developed WPaxos. We tested it with TLA Plus first. It helps us a lot, right? So it helps us to tune the protocol, figure out the protocol, understand its correctness better, and present it that way. In our paper, we present the Pascal pseudo algorithm because that also helps us, right? Instead of inventing a new pseudo algorithm notation for each case, just write it in Pascal, give the Pascal code so the reader can go, play with it, extend it, modify it, and check that our claims are true.
So in your workflow with TLA, are you in some sense experimenting using TLA?
Yes, I think of it as exhaustively debugging the design,
Okay.
right? Exhaustively debugging the protocol.
But it comes in pretty late in your algorithm design stage.
I have a concept in mind, then I write in Pascal. When I'm writing, it basically tells me that actually this part was vague. Now, what do I do about it? It helps, but first I have a concept, and then I start modeling, and then the modeling helps a lot because it says, well, you hand-wave this in your mind, but this becomes a problem. Here are the counterexamples for it. Yeah.
So among academics in that world, the algorithms, do you find this to be common to use TLA?
It's catching wind, but not common. I teach it in my distributed systems class since 2014. Students like it. It has a learning curve, but now more examples are being available. I also make more examples available in my course. It gives them a hands-on thing to experiment with these algorithms. Otherwise, when you are teaching the algorithms, they again see the happy path. They say, okay, the algorithm, it works. They don't see why it works and how it breaks. But when you give the model to them, they can try it themselves and see why it works and how it breaks. And this is also good for giving class projects, because if you give a real implementation projects, let's face it, I mean, distributed systems are hard implementing. There are more things. They get bogged down with the implementation specific details. They don't learn as much about the protocol details. This, they can experiment at the protocol level. So I give my class projects at the protocol level to teach them more about the distributed algorithms and the concurrency, and not necessarily the implementation languages also change. Frameworks change, but if they get the hang of concurrency, how the files can cascade, that's more useful.
So, what kind of aspect do you think in the distributed world that TLA Plus cannot model?
What it cannot model?
Like if we're going to,
Right.
for my team, if we're going to introduce this for everything, so what's kind of disadvantage do you think we have? So it looks like it's kind of like it's a perfect test process, right? You can verify thinking almost everything. So
Right, so it can be used for several things. I think you get the most mileage out of it for concurrent systems, because it interleaves different executions at different times that you didn't
Yes.
think of and gives you counterexamples. So if you have some concurrency, it's very good for it. But I mean, to think of limitations, if this is a component in a complex sea of other components, right? And if you want to test the thing, you need to have a lot of modeling done before testing this with fidelity. But even testing at high-level abstractions, approaching different ways. So I said that we test the lease protocol separately, right? Still, you get insights from that. But yeah, maybe the barriers would be, first of all, figuring out the right abstractions to test. And if the environment is complex, maybe first figuring out what are those and modeling them. Marcus, do you have something to add?
Well, there are multiple use cases where TLA plus has been used, which are kind of surprising. If you, for example, look at the TLC source code, this translation from Pascal into TLA plus, this has been modeled in TLA plus and then implemented in Java.
Interesting.
It's kind of surprising, right? Same for the parser that parses the TLA plus into the syntax tree that has been modeled in TLA plus first and then implemented.
Right. I mean, there is even an attempt I see on GitHub from translating directly from Pascal to Go. That would be nice, but it's limited probably now. But I think for a domain-specific application, right, it's doable. If you have only, maybe up to 100 primitives, functions that you use, you can just translate from Pascal to that, if that's possible. Does this make sense? Maybe if your domain is specific, not generally, it will be hard to do. But if you work in a limited domain, like chip design, or if you work in a limited domain, like database interactions with a set API with respect to things, then you can maybe even think about generating code directly from this. Then you would, because there is right now a mismatch, right? This helps you get the design right. But then you embark on implementation. And this is where the testing methods fit again, right? You get the design right. At least you don't have to worry about it. But when you implement, test. And with this model now, the invariants can be helpful as input to your test to see that does your implementations really satisfy them? If not, where it fails to satisfy them. But you still need to test because your implementation is divorced from your model. Yeah. You need to make sure that, or you can, if it's domain specific, limited domain, you can say directly generate code from there. But otherwise, I guess to answer your question, another obstacle is that this thing about design and implementation, this gap. But still, it's very useful to exhaustively debug your design because you get rid of design bugs. You don't make them in your implementation. You got rid of the expensive to change decisions. The other decisions are easier to change because they are implementation decisions.
Do you have experience with any other languages than Pascal that goes to TLA plus?
No. I think Pascal has two flavors, Pascal version Pascal. And C version.
I saw there, I know 2 attempts to use a different language that is much more, I would say, expressive.
I see.
And they compile to TLA plus and check the results.
I think that would be interesting. I mean, it's reading the TLA plus code helps. You can see how the logic works. The logic works is, this is all state transitions, right? You pick one process, you pick an action in that process, and that action changes the variables, the state in a set way. And having that helps because that steers you toward invariant-based reasoning because it can pick any process and it can pick any action. But if you reason at the state level about what are the allowable states that the program needs to be in, that's a useful mode of thinking for concurrent systems. Okay, that's
Thank you.